Okay, so looking at exponential functions, we have mainly two types of exponential functions. We have growth and we have decay. Now, visually, they're very easy to tell apart. A growth function it will be increasing from left to right, and it would look something like this graph. This is the x and the y-axis. So what you'll notice is it's very flat or almost level on this side of the graph. Oh, this doesn't erase like what it normally does. But on the other side of the graph, it's increasing very, very steeply to the fact where if it keeps going, it almost looks like it's going straight up and down. So that's growth. Now decay is the opposite of this. Decay is a graph that drops down from left to right. And it has essentially the same properties, the fact that it levels out near this side and then it just increases really sharply on this side. Now, as far as equations go to tell them apart, exponential growth would be an equation similar to, let's say, y equals, well, it's typically written as a times b to the x power, but essentially what you'll notice is like numbers bigger than 1 to the x power, so like 2 to the x power, or 3 to the x power, or 4 to the x power, things like that, of course, would be exponential growth. Exponential decay would have numbers that are smaller than 1, but there's no such thing as negatives here. Well, at least for the b value. And anyway, I'll talk more about that in a second. But a decay function would be something like 1/2 to the x power, or 1/3 to the x power, or some kind of decimal like 0.8 to the x power. That's the kind of thing you would see with exponential decay. So if you see a graph that's going upwards, look for, exponential growth, as in you have a number bigger than 1. So when I say b value bigger than 1, I'm talking about this number with the exponent of x, so the 4 in that case. But if it's decay, if your graph is going down, then look for a b value that is greater than 0, because it won't be negative, but still less than 1. So some kind of decimal or fraction would be exponential decay. Another thing to point out is kind of a different way of writing exponents and radicals. So there's this general rule. So if you have a radical with a number in it, let's say the number is, I'll just call it x. It doesn't really matter. We'll use numbers in a second for an example. But it might be the eighth root of x to the b power. So what we have here, now I'm going to make this look a little bit better. X to the b power. So a is called the index number, and b is, of course, the exponent. X is just going to be like your standard normal number. But b is the exponent on x, and a is the index number for the radical. So what you'll see, let's give you an example, is let's say maybe you have the cube root or third root of x to the 5th power. Another way of writing this would be x to the 5/3 power. So the general rule is you would have the base x, or whatever your value or your number is, and then the exponent part would be the numerator, and the index part would be the denominator. So it's just a matter of don't get those mixed up, okay? If you get those mixed up, then you're in trouble, right? So here you can see that my exponent part is my numerator, and my index part is my denominator. So let's just show you a couple more, right? So let's say you have the 4th root of x to the 9th power. This would be x to the 9/4 power. Remember, the exponent here is the numerator, index is denominator. So exponent equals numerator, right, or top, and index equals bottom. Now, one thing we might see is, what if one of those numbers is not visible to us? So for example, let's say I have cube root of x. Let's say it doesn't show us any exponent here on x. Well, it doesn't mean it doesn't exist. It just means it's x to the first power. So what this will look like, it'll be x to the 1 over 3, or x to the 1/3 power. So if you had the 6th root of x, this would be the same as x to the 1/6 power. Something very important to keep in mind. So if you have a number, let's use that actual number. Let's say 16. Let's say I have the 4th root of 16 to the 3rd power. Another way you could write this is simply 16 to the 3 over 4th power, right? Where again, the numerator is on top and the index number is on the bottom. More exponent rules would be if you have, let's say, an exponent with another exponent, that you kind of have a double exponent thing going on, those numbers can be simplified by multiplying together. So essentially, x to the 2nd power to the 3rd power is the same as x to the 6th power, where you can multiply those values together. So if you, let's say you had y to the 2nd power to the 5th power, right? The two exponents can be multiplied to simply write y to the 10th power. So an exponent on top of another exponent can be multiplied. And if you have two things, let's say I have ab, let's say b to the 2nd, ab to the 2nd to the 3rd power, then both of these things inside those parentheses are getting essentially cubed, right, to the 3rd power. So you'd have a that goes to the 3rd power, and then b with already has an exponent means you're going to multiply those together. So that would be b to the 6th power. Okay. So if we had, let's use a, b again. Let's say I have a to the 2nd power and b to the 4th power. And then I said this was to the 5th power. Then I would have the exponent getting multiplied to both of those other exponents. So this would be a to the 10th and b to the 20th. Okay, but if I make it a little more complicated, let's say I make it with fractions. You know, if I have a to, well, again, I'll use a. We'll leave a alone, and then we'll say b to the 3rd power. But then this goes to the, let's say 2/3 power. Same philosophy still applies. This goes to both terms. So essentially you have a to the 2/3 power, and then b to, and then you have to multiply the 3 and 2/3 for b. So 3 times 2/3, 3 times 2/3 would be essentially just multiplying like across 3 over 1 and then 2 over 3 would be 6 over 3, or simply just 2. So it would be b to the 2nd power. Well, that would be our result. However, keep in mind that this can be written in radical form. This could be written as the cube root of a to the 2nd power, and then you can still have b to the 2nd power. And so what I did here to go from there to there was I did that property we were just talking about a second ago of having, you see these, how the index number is a numerator and the exponent is the numerator and the index number is the denominator. I'm essentially using that property but backwards, right? So the numerator 2 is the exponent, the denominator here is the index. So it can be rewritten like that. So let's practice that a little bit again, just to remind us. So if I have x to the 4/5 power, this could be rewritten as 5th root of x to the 4th power again, where the denominator is your index and your numerator is your exponent. If you have x to the 1/3 power, again, this would be the same thing as just the cube root of x, where the denominator is your index number and the numerator is your exponent. But you wouldn't write x to the 1st. You could just leave it as regular x. So essentially it is still x to the 1st, but you won't really write that. You usually just write the cube root of x. And you kind of have it be that. I'm trying to see if there's anything else I really need to talk about. I know there was I think there's going to be something. So one use of exponential functions is through financing, particularly, especially compound interest. So there's a compound interest formula called A equals P, and then it's 1 plus R to the T, or sometimes people use N there. And so what this means is A is essentially like a Y equals, kind of your answer at the end. Now, P is going to stand for the principal, which is kind of our key for starting amount. R is our rate, and then T is for time. So an example is if I say I'm going to have a loan of $50,000 and that it's a 5% rate for 3 years, I would use this formula as such. The start value is my $50,000, so I'd have A equal to $50,000, just plugging in the numbers. The 1 plus R would be 1 plus 5%. But here's the thing, 5%, you're not going to write it as 5% in here. Okay, you're actually going to have to change this to decimal. So you can take this number and divide it by 100, and that'll give you the decimal version of it that you really need. Think of it like change. It's 5%. Think of it like 5 cents. How would you write out 5 cents? 0.05. So that's another way of doing it. You can divide it by 100, it's 0.05, or just remember that percents are like cents. Percent, cents, right? 5%, 5 cents would be 0.05, right? And then it'd be to the third power for time being 3 years. Now this would simplify because 1 plus 0.05 would simply be 1.05. So you might see that. Just kind of be aware of how it gets there. So if I saw something like if I had an equation that read 200,000 and then I saw 1.12 to the 8th power, I would know that from this problem that my starting amount was 200,000. My rate is 0.12, which 12 cents is the same as 12%, so it'd be a 12% rate, and that this would be 8 years or months or whatever it is, the unit of time in the problem. Typically it's years, but yeah, that represents time. So you kind of have to just kind of recognize things like that as well. It can really help you out. I strongly recommend what you do here is maybe, rewind the video or just rewatch it all again. Maybe, take some notes, do what you got to do. When it comes to looking at graphs of things, try to plug in numbers. So, for example, let's say I have a graph that looks like this, right? Now, the first thing I'm going to notice is the fact that this graph is leveling off at -2. It's not going to go below -2. It's going to level off at -2. Or I don't know if I have. I don't have any kind of graph paper on this thing. Let's see. If I have a graph, try to make this as good as I can. It's not gonna be perfect, but it'll work. See, 2, 1, 2, 3, 4, 5, 6, 7, 8. We'll say right there. We'll say it's 8. So look at points on the graph, for example. So like when I look at this graph, I'm gonna notice I have a point that's easy for me to see at 0, 1. I have a point that's easy for me to see at 1, 2. And I have another point, which again with a better graph, but let's say it's easy to see and it's at 2, 8. When I look at my choices, when I look at my options, I can try taking my options and plugging in certain numbers. So when I have my options, let's use these points that I can clearly see and see if any really, oh, this would probably be 4. Okay. Again, I'm kind of doing this pretty quickly. That might be it, right? So I'm looking at these points, and then I'm going to think, well, can I plug in any of those x and y values to see something work? So for example, these would all have the 0.01 on them, because anytime you have, let's say, 2 to the 0 power, or 1/2 to the 0 power, or 3 to the 0 power, anytime you have a power of 0, an exponent of 0, all of these are equal to 1. So anytime you plug 0 in, you're going to get 1 out as a result. So 0, 1 is a pretty common point for this. But plug in something else. What if you plug in 1? If you plug in 1, right, this would be 2 to the first power, which is equal to 2. So you'd plug in 1 and you get out 2. This one would be 1/2 to the first power, which would be 1/2. So you plug in 1, you get out 1/2. And then the last one here, if you had 3 to the first power, you'd plug in 3, this would equal 3. So you plug in 1, and you get out 3. So you're looking for points. Now this one, 1, 2, was on my graph here, so that's looking pretty good for this answer choice. But if you want to go one step further, right, plug in the next number. What if we did 2 to the second power? Well, 2 to the second power is 4. And so when I plug in 2, I get out 4, which is also on my graph again. So it looks like this fits, right? It looks like that's the graph of that equation, right? So you can do things like that as well to sort of help you find out graphs. And that goes for anything, not just exponentials. That's how graphs work in general. So you plug a value in, you get a value out, and that creates a point. So if you can find points on the graph and use them to your advantage, that would work out. So that's basically everything that I can come up with. If there's anything else, like let's say I have the fourth root of 12, and this is to the 1/5 power, right? Remember how this would still be the numerator, 1/5. This would still be the denominator for 12. It'd be 12 to the 1/5 power over 4. It kind of looks weird being a double fraction, but essentially it's 1/5 over 4, like 12 to that power. Now, all you have to do in this case is multiply these denominators. Essentially, it's the same as 12 to the 1 over 20th power, right? Or if we have something like the cube root of 18 to the 1/4 power, this would be the same thing as 18 to the 1/4 over 3, which again, if you just multiply those denominators there together, the 4 and the 3, you end up with 12. So the same as 18 to the 1/12 power. Things like that, still work even with fractions. So be aware. I hope that helps. This is the best I can really do. I know it's not a lot, but it's a little. But yeah, if you guys need anything, just let me know. We'll cover more of this in more detail later on in the upcoming weeks after spring break. But this is just a little brief introduction to it now. All right, I'll see you guys in a bit. Bye.